Hi, in this video, we want to take a look at estimating correlation. And we're going to be working through time series analysis and its applications. Section 1.5, estimation of correlation. Here are the authors of the textbook. Here's our GitHub page and information about the package that goes along with the textbook and where we're going to be using a lot of code and functionality can be found at these sites. All right, and the textbook can be downloaded for free by UCF students through the library. All right, so what we're interested in doing is checking to see, do we have correlation of a time series with previous or future observations of itself? That's the autocorrelation. We also want to be able to check the correlation between two different time series. And we'll also have a lag aspect of time series and time series in the past, or a time series and a future value of another time series. And so that'll be the cross correlation function. Now, when we talk about covariance and correlation, we're actually measuring the same thing. Covariance, though, is easier to work with from a pencil and paper theory point of view. So covariance is really important theoretically, but when I sit down and actually work with data, it's not as useful. When I start talking about correlation, correlation is usually what I'm going to be looking at when I'm looking at real data. So the reason why there's a distinction is that correlation is between -1 and 1, of course. That's well established at this point. And covariance, we know, is going to be bounded by the variance of what's going into it. But I don't know, like, what's just looking at the covariance by itself and not knowing anything else. I don't know if that's big or small relative to the project I'm working on. And so when I'm doing a real life data project, I'm going to be looking at correlation almost exclusively. But we use covariance to get to correlation. So we're going to be looking at both of them at the same time. All right, so here is, I've commented out the code, but if you want to get all of the information and everything about the package, to download into your R session, here are the code that you need. And here I'm setting up just some features of my workspace to limit the number of digits that are printed. This sets it up so that I prefer to not use scientific notation. And this gets rid of any artifacts that I've got floating around. If you run this, this is going to delete things in your work session. Don't use RM unless you want a clean workspace. All right, so in previous videos, we focused on autocorrelation and cross-correlation, and we looked at it theoretically. Now here, we're going to shift our focus to when I have actual data in my hand so that I can look at what I have and figure out what's going on. We're going to estimate the correlation and the covariance in this one. And so one thing we're going to do, just like with regular old statistics, when I've got my time series, I'm going to look at the mean. So just like we would do with any other project, we're going to look at the autocovariance and we're going to look at the autocorrelation of our time series. Now, when we use the mean, we're going to be, anytime I'm using the overall sample mean, I am either investigating or I'm assuming that we have stationarity of our time series. So in real life, most of the time on time series, we will not have IID, independent identically distributed observations. So what we're going to do, we're going to make the assumption that we have stationary data, and then we're going to move forward. And so if I have this as an assumption, then I'll be able to make estimations on means and covariance. If I don't have this, if it looks like from my data I don't have stationary data, then I need to use other techniques. All right, so something that is important is that anytime I'm using a sample mean, an overall sample mean independent of time, then I'm making the assumption that we have a stationary time series, or I'm investigating a stationary time series at that point. All right, so just like with basic standard statistics, I'm going to take my sample average, and we know that the sample average expected value is going to be the expected value of the population overall at the same time, and it's going to have lower variance than taking the individual values to estimate the expected value. And so then, if I take the variance of my sample, that's of course the variance. There's variance of my sample average. Here's the variance. Well, one thing that we can do, we can look at this as actually the same thing as the covariance function. So here I'm taking the variance, and I'm realizing that this can be written to be equivalent to a covariance statement. And so then I can rewrite my variance this way. And so I'm showing the connection between my covariance and my variance estimate with this calculation. So now, if h is equal to 0, then I'm going to be getting the variance. If h is not equal to 0, then all the terms, when I have white noise, because of the independence, we're going to have covariance of 0, and all those terms disappear and fall out. And so we can see, boom, this gives me my variance statements. Now, something to realize is that the variance of x bar may be larger or less than this when the covariance terms are non-zero. So when I have, imagine a situation where I'm in a time series where we get the same value every single time. Maybe the first value is random, the rest are just repeats. When I have a covariance like that, the variance aspect can change quite a bit. All right, so now sample autocovariance. Well, what I'm going to do is I'm going to just take, for the autocovariance, I'm going to take the sample average in both spots. I'm going to subtract off the 2 points in time that are of interest in the individual product. And so here I have a point in time and point of time with the shift of interest at that, multiply the whole thing together, and I'm going to add up over all the values of t, and I'm taking the average. All right, so now two properties that we have about this is that this is symmetric about 0. Also, this is a biased estimator, and it's biased because of the aspect that we have up here. All right, so our sample autocorrelation function, what I'm going to do is just run through the same thing I did before in the previous video for autocorrelation. Remember, I'm going to take the fraction where I've got autocovariance up top. I'm going to take the square root of the covariance times the autocovariance. That will be 0, 0, and HH. Remember that when we're talking about shifts and I have the same value, it's when we have a stationary assumption, then it's about the difference in the values, not the actual time itself. So the difference in time is important. If I have HH down here in that square root, what's going to end up happening is it's equivalent. The covariance of HH is the same as covariance of 0, 0. I'm multiplying something by itself, the square root cancels out. Boom, we get this nice little pretty fraction. All right, so now let's go ahead and do a sample autocovariance function and the scatter plots. All right, so estimating the autocorrelation, similar to estimating correlation in any other situation we're on. It's just now, every time when I have time series, I have to potentially consider the correlation of a time series with itself and any other lag time point. All right, so what we're going to do, I'm going to take, this is the amount of lag, and H is the lag, N is the number of data points I have. Then I'm going to have N minus H pairs of points I could potentially get. And so then I'm going to, take my data, shift, and then I'm going to compute that correlation for the n minus h points, pairs of points. All right, so let's do an example. Let's take the SOI data set. This is the Southern Oscillation Index. And so here's some information about, for our purpose, we really don't care that much about the story behind it. We care about what we see with the computations, because that's what we're focusing on in this video. Here I go ahead and I load the data. And here I'm following the author's example. We're going to go ahead and do a max lag of 6 and just see what we get for the autocorrelation. And so here we can see that here's a, the first lag, then it goes down to here and there, all the way down to that. And once we get down to this random noise aspect here, we will more than likely, we would treat this one as just random noise. It's just a little bit poking out. This one, there may be something that's statistically significant, maybe not. I would have to use like further insights, use the story of what's going on, subject matter expert information, and maybe increase the max lag to figure out if this is just random fluctuation, or that's just random fluctuation that's just poking out, or is there something going on? Is there more of a story? All right, so now let's go ahead and do a time series plot. And here we're going to be taking the lag. So here with the lag function, this is in base R. I'm taking my data and I'm shifting back by 1. Here I'm taking the original data without a shift. And here this is just plotting parameters. And we can see that overall we have a 0.6 correlation between the data and 1 shift back. And so here we can see that there is a overall linear trend. 0.6 is not very strong for the purpose of making predictions. Notice how big of a cloud this is. Now, visually, I definitely see a trend, but notice that if you were to tell me that the lag of -1 gave me 0.5, I'm realistically seeing something in this full range, this vertical range of observations for coming up. That's a pretty wide range. And so that's why it's only 0.6. All right, now let's go ahead and take a look at -6 for our lag, for our shift back in time. And now here, when I plot it, so here I've got observations from 6 time steps back. Here is the current observation on the y-axis, and we see we've got a -0.2 correlation. And when I look at that, I just see clouds of dots. I don't see any real trend. Like, yes, I can see that if you were to say positive or negative, I would say that there's a negative slope with this just because of how things are kind of clustering. But overall, I would say if you showed me this and I didn't see this number, I would say nearly 0 correlation. All right, so now let's talk about the large sample distributions of autocorrelations. All right, so one thing that we're going to do in statistics over and over and over is that if I have a large enough sample size, then in the idea of mathematical convergence, I know mathematical properties, mathematical statistical probabilities of what's going to happen. And so I've got an idea of maybe expected value, maybe variance, maybe distribution when I have large samples. And so what we'll do is when I'm working with my data, if it looks reasonable that certain assumptions hold, we'll go ahead and say, hey, I'm going to work with things assuming that that large sample approximation is going to hold for what's going on. This is, in a lot of ways, this is filling in the blanks of what my data is not telling me. If I have a huge amount of data, I don't need to make large sample assumptions. If I have small data, I'm going to make larger assumptions to fill in the blanks so that I have something to work with, some way to make progress in my project. Because if I can't make progress in my project, I'm dead in the water, I'm going to get fired, and I'm going to have to find a new job, which should suck. All right, so if we're dealing with IID white noise with a fourth moment, so when I say it has a fourth moment, I'm also saying it has a first, second, and third moment. And so an example of this is white Gaussian noise. If we assume that n is large and h is fixed, that should be lowercase h, then the sample autocorrelation, rho hat, for 1 through capital H, oh, sorry, I misspoke, this is capital H. So this is the range of possible lags, is approximately normally distributed with zero mean and standard deviation given by 1 over square root n. All right, that's nice because now I have a probability distribution for my autocorrelation. Now, using the approximate distribution, we obtain a method for assessing whether peaks are significant by determining whether the peak is inside or outside the interval. So if it's in using normal distribution, whatever level of confidence you're interested in, you can change what the numerator is, that plus or minus, like plus or minus 2.5, plus or minus 3, depending on your project, plus or minus 1.96. But as a general rule of thumb, plus or minus 2 over the square root of n is a good, reasonable cutoff for assessing if a peak is statistically significant or not. All right, so for a Gaussian white noise sequence, approximately 95% of the sample autocorrelations will be within this interval. All right, so why is this IID white noise assumption reasonable? Well, it's going to work out that in a lot of situations that for our statistical modeling, it will be reasonable for us to reduce what we're looking at into a time series of white noise series with various kinds of transformations. And so what we're going to end up doing is we're going to use white noise time series as the building blocks for what we have. And if that's a reasonable way to approach the current time series I'm looking at, then I can invoke other theory to fill in those blanks for me so I can make more progress. All right, so now let's go ahead and look at an example where we're going to simulate a sequence of coin tosses. What we're going to do is I'm going to flip a coin repeatedly. I'm going to put down a +1 for heads, a -1 for tails. All right, that's going to be my X time series. Then I'm going to create another time series. We're going to call it Y, and that is going to be 5 plus the same time points for X minus 0.7 times the previous X value. All right, so X is going to be plus or minus 1, and here, and it's going to be plus or minus 1 for the previous observation, and then we're going to make Y sub t. All right, so it's going to work out that using the standard covariance formula, we can see that the true theoretical correlation for this is going to be approximately negative 0.47. Right, and this comes from the direct calculation because in a previous video we went over the formula to compute this type of covariance. Now the x's are independent, and so the covariance is 0 when the shift is greater than 1. So when you sit down to do the calculation on this covariance, because of the IID aspect, they're independent, identically distributed. What's going to end up happening is that when I have 2 points, like here, when I've got overlap, I'm going to have the number of overlapping terms in the covariance computation. So it'll be 0, 1, or 2. That's the number of non-zero terms in the covariance summation. And so once they get outside of each other, so I'll have here, 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 and then nothing. And then it's always going to be, the covariance will be equal to 0 every single time. All right, so what we're going to do, just to show some examples, we're going to generate two data sets with different sample sizes. Now notice that the smaller sample size is going to have different cutoffs than the larger sample size on the dash bar on the autocovariance plot. All right, so for the smaller sample size, here I've got a total of 11. So with a shift, that's going to be a 10 if I'm shifting back by 1. And then the filter function gives us our y. Here's our overall average. And notice that that's close to 5, by the way. And here is our plotted time series. And this is the author chose to make this look like stair steps, which seems reasonable for this one. And here is our autocorrelation. Now, notice how high up this dashed line is and how low it is, how much higher up than the next one it's going to be. So here it's going to be pretty wide for random variation. So since I have a small sample size, it would take a very strong signal for me to conclude that something is statistically significant. I've got 11 points of data total before shifting. Therefore, I don't really have a whole lot to go off of. It would take a very strong signal for me to say, hey, I have something statistically significant. Now, on this next one, we're going to kick it up a notch. We're going to go ahead and increase the sample size to 500. Same code otherwise. Now, notice that this is a lot closer to 5 than the previous one. I had smaller sample size, and so my estimation of the overall average wasn't as good. Now I've got more data, and you can see that's way closer to 5 than the previous one. We're going to run through the same thing, and I'm going to plot. Now look, this is a very crowded plot. Initially, I actually had 10,000 points in the data generation, and this was just a black box. There was just so many points. It was just too many with the vertical lines going between dots. So I went ahead and just reduce it down to 500. When we look at the autocorrelation, notice how tight these dashed bars are, the dashed lines are around 0. That's because I have greater sample size, which means that my system is going to be more sensitive to detecting statistically significant autocorrelation. So there can be pretty small autocorrelation going on in the system, and potentially I could detect it. Now here, this looks like noise to me. Beyond this first one, I'm saying, hey, that's just all random noise. And so in most situations, when I see something like these, comb teeth just kind of sticking up, sticking down, and I don't see a trend, once I get down to random noise, I conclude the rest are random noise. If it looks random on which direction it's pointed, and I get below the dashed lines, then I believe there's no more autocorrelation going on, and which I know is correct because I generated the data. All right, so here, same idea, slightly different values for this, slightly different setup. Another version of the text approached it this way. The author included this on their webpage, so I'm showing it now. And here we can see these results. I'll just scroll through a little so you can see it. Once again, on the first one, you can see much wider range needs to be crossed to be statistically significant. And then here, that shrinks down when I have a larger sample size. All right, so now let's look at the autocorrelation of a speech signal. All right, so we're going to compute the autocorrelation function from an example you looked at previously, where we're going to take our time series and match and look at the autocorrelation with h units into the future. All right, so It appears that in the speech example, it's going to contain a sequence of repeated short signals, and the autocorrelation function is going to confirm this, showing peaks spaced about 1.06, or sorry, 106 to 109 points away. And this difference, this for the repeating signals, it's known as the pitch period and is a fundamental parameter of interest in systems that encode and decipher speech. Now, here's information about the data set that's being pulled from R. I copied and pasted this from R. And so it's sampled at 1,000 points per second. And the pitch period is between 0.0106 and 0.0109 seconds. And to compute this, to figure out the autocorrelation, we're going to use the speech function with 250. All right, so here I am loading the speech data into my workspace, and I'm just dropping it straight into the autocorrelation function, and with a max lag of 250. And here, even if I saw, so even when I look here and I see that it's under that dashed line, because I'm seeing a pattern of what's going on, I believe that there's something happening, even though the autocorrelation using that IID assumption, even though it's below that dashed line, I believe that there's something actually happening because of the pattern I visually see. All right, now let's talk about cross-covariance and cross-correlation estimation. All right, so when I have cross-covariance, cross-correlation, I'm interested in two separate time series, and I want to get the correlation or the covariance between one time series and a lagged version, a shifted version of the other one. And so what we're going to do, we're going to take one of our time series, we're going to say, hey, you stay put. The other time series, we're going to shift as appropriate by the right amount. So you'll notice that in the computation, this is with t, so here we're saying that y stays put, x is getting shifted by h. Now, something that is important to notice is that if I'm using the overall average for these, I'm making the assumption that we have a stationary mean. So I'm assuming weak stationary for both of these for this to make sense for this calculation. Now, once I have the cross covariance, I can very naturally go ahead and take the cross correlation by rescaling by the appropriate values in that square root. All right, so to estimate these, what we're going to do is, in a very natural manner, I'm going to compute my covariance the same way I would for any other covariance problem. It's just that what is, like, which points go here? Oh, this should be a y sub t. That is an error on my part. That should be y sub t. And, standard way of computing covariance. Now, the reason why we don't really like covariance when we're looking at real data is that I don't know if this is big or small, honestly, just looking at the number by itself. So what we want to do, we want to rescale it using the correlation function very naturally. So I'm going to take the sample covariance, and I'm going to divide by the unshifted covariance, variance, square root, multiplying the two together. And we know that that's going to be between -1 and 1. Since it's between -1 and 1, I've got benchmark for what is big, what is small, and I can reach a conclusion. When I'm doing pencil and paper theoretical work, this fraction aspect gets in the way. It's kind of a pain. And, I've got 3 estimated values in there. I've got a fraction. I've got 2 things on the bottom of that fraction, and there's a square root. It's harder to get to when I'm doing my theoretical work. So as much as possible, if I need a theoretical conclusion, like in a proofs class, I'll use covariance, but when I'm working with real life data, I will use correlation. All right, so we will In general, we're going to look at this graphically. We're going to use our eyes to make a decision about what's going on, and we're going to treat the cross correlation as a function on the lag between them. All right, so now the large sample distributions of cross correlation. So if at least one series is independent white noise, then the large sample distribution of my cross correlation is going to be normal with mean 0 and 1 over n as my variance. So my standard deviation is going to be 1 over the square root of n. All right, and so now let's go ahead and look at an example. And this is example 1.28. This is once again, we're looking at the SOI and recruitment data sets. So the autocorrelation and cross correlation functions can be used to analyze the joint behavior of the two time series together. All right, so we consider the simultaneous monthly readings of the SOI and of the new number of fish computed in the model. And in a moment, we'll look at the autocorrelation and cross-correlation functions. Both autocorrelation plots show periodicities corresponding to the correlation between the values separated by 12 units. Observations 12 months apart or 1 year apart are strongly positive correlation, and so are multiples of 12. All right, so I think that there's something going on a seasonal aspect. Observations separated by 6 months are negatively correlated. Oh, okay. All right, that's something to pick out, showing that the positive excursions tend to be associated with negative excursions with a gap of 6 months. The cross-correlation plot, however, shows some departure from the cyclic component of each series, and there is an obvious peak at lag of -6. The results imply that the SOI measured at times t minus 6 months is associated with the recruitment of time t. All right, so when I look at the SOI 6 months into the future, we're seeing something going on with recruitment. And so we're going to say that SOI leads recruitment by 6 months. All right, so the sign of the cross-correlation function is negative, leading to the conclusion of the two series move in different directions. That is, an increase in SOI leads to a decrease in recruitment and vice versa. Now, in the next chapter videos, we're going to see that nonlinear relationship will be discovered between these. Now, for this particular plot, we're going to see that the dashed lines are going to correspond to plus or minus 2 over the square root of 453, which is approximately 0.1. But since we know, looking at the system, I know that these are not just like noise, white noise series. Therefore, these lines are not useful to us. So how do we actually get this to come out? All right, well, first I'm going to load my data. Then I'm going to look at the autocorrelation function for SOI. And I can see a clear pattern. So once I see this pattern, I know I don't have white noise. These dashed lines do not apply. Very clear pattern going on here. Now here's recruitment. And once again, we're seeing a pattern coming down. Now let's get the cross-correlation function going. And here we definitely see that there's something going on with a pattern here. And so we're going to focus on the fact that we're seeing peaks about 6 months apart overall. Now, it's not exactly 6 months apart in a lot of spots, but overall, on average, when I look at this, I'm saying 6 months apart is about where things are, changing on these peaks. All right, so now let's go ahead and talk about the concept of pre-whitening and cross-correlation analysis. All right, so let's talk about the pre-whitened series. All right, so to use a large sample distribution of cross-correlation, at least one series must be white noise. In the previous one, we knew it wasn't. If this is not the case, there's no simple way to tell if a cross-correlation estimate is significantly different than zero. All right, visually, we are concluding that there is something going on, but down the road, when I look at other data, I have no real simple way. I have to somehow pull in information to figure out what's going on. And so if I know that I don't have white noise going on somewhere, then I am, we lose our, many of our tools. All right, so in this particular example, we go ahead and we make a guess that we have a linear dependence relationship between the two. So just to explore, just to see what's happening, look at something interesting to get more of a theoretical understanding of what's going on, let's go ahead and let's generate two time series that look similar to the SOI and the recruitment time series. So what we're going to do, we're going to say that X is for a cosine time series plus Gaussian white noise. We're going to say that Y is shifted, see, off, and cosine once again plus white noise. And we're using Gaussian white noise, and we're using standard normal for this example. So let's generate two time series off of this, and let's look at these plots. All right, so we're going to have so the first two plots are going to show the generated data. This is going to be the first two. Then the middle two figures that we look at are going to show the autocorrelations, and we'll see that we're going to get a cyclic nature of both series. Now, the second to last plot is the cross-correlation plot, which appears to show cross-correlation even though the series are independent. We know that they're independent because we created them, we built it, we know what's going on. The last plot, and this is the important one for this example, is going to be the pre-whitened version of y sub t, and we're going to run the cross-correlation. And we're going to see that the two series are actually uncorrelated, even though it looked like they were at first glance. And so what we're going to do, how do we get pre-whitened, is that I'm going to take y sub t, and I'm going to take cosine. So instead of doing cosine shift, we're doing sine, which is appropriate if you remember your trigonometry. Remember, sine and cosine are shifts of each other. So we're using cosine and sine, and we're going to do regression. And then I'm going to take the residuals off of that, and we're going to work with it from there. All right, so here, doing my random number generation. So setting the seed so I can reproduce the results in the future. Have 120 data points. Here, t is going to be my time. X is that cosine function with a random term. Y is cosine with a shift, and then normal. And then here, I'm taking a linear model. I am taking the y time series, that's the shifted time series for cosine. I am going to do regression with sine and cosine. Remember that this sine here is equivalent to a shifted cosine, so I'm addressing that shift by itself already. And then doing a linear regression model. And then I'm grabbing the raw residual. This is not the studentized residual. This is not the standardized residual. This is the raw difference between observed and modeled values. And now let's go ahead and start doing our plots. So here is the X. Here's the Y. All right, so I mean, just looking at it, we kind of see a pattern going up and down, up and down, up and down. The noise is definitely, polluting that cosine aspect. Here we see the Y. I see something that looks similar, just shifted a little bit. Actually, to show the shift, notice that this is starting higher up and then going down. This starts like down is going up. All right, so now let's look at the autocorrelation function on lag. So here, lag is the horizontal axis and the vertical is the autocorrelation on X. And we definitely see something that's going on. We see a pattern. I see something similar going on with Y. Here is the cross-correlation function. So I see that cross-correlation function like, hey, I must have something going on. And in fact, no, it's just that the series are just independent of each other. It's happened to, just be that way. When we go through and do the whitening, so for the whitening, this whitened version of Y, I'm looking at the residuals after doing regression on sine and cosine. I can see there's nothing going on. Everything is well within the random noise band. Now, here's another example that the author gives. If we just work through this, we end up getting the same result. Get back to the code to generate it. All right, well, that's all I've got for you. Take care and goodbye.